Hello, this is Dr. Liu. In this video, I want to give you an overview of all these SDI12 USB adapter lines of product. So let's start with the very first one, the basic. So, so this one is the basic USB to SDI12 adapter. We have a number of SDI12 connections, external power, and the selector for the external power. We have the USB chip and also the processor. So this is very basic. It is the cheapest, but it also is expandable. It has a number of options as well. For example, this option right here, there's actually an option where I will solder this thing on after checking all the connections electrically. So this connector will provide you up to 4 channels of basic analog input. This is 10-bit analog input. The accuracy also depends on the USB power's voltage, so that's why it says basic. And it also could act as digital on-off inputs. And more interestingly, it can also act as a digital pulse counter for things such as flow meters that are outputting pulses, and also water rain gauges that output pulses. And I even have just recently come up with this tiny little circuit here. It is small enough to be in line with a sensor such as a rain gauge. What it does is it smoothes out the rain gauge output. The rain gauge output is actually mechanical. It is using something called a reed relay. So whenever there's a tip of the say a tipping spoon that tips over to release the water, the pulse is not actually a single pulse, actually a number of pulses. So this little circuit will be able to help you filter that out into a single pulse, and then you can have that in line with one of the channels. I know that you probably don't need 4 channels for rain gauges, but you can use one of them for rain gauge, and the other 3 you can use them still as basic analog inputs or digital inputs. But that's an option that you can put in here. And so that is the basic adapter. So now let's move on to this fancier adapter. This is the USB SDI12 Plus analog adapter. So it has all the features, well, except for the extendability. It doesn't have the extension. It has the features of the basic adapter, and at the same time it has the analogs. So this chip here provides 4 channel of analog input at high resolution, 16-bit of analog single-ended resolution. And if you prefer a differential input, this also provides you differential input up to 2 channels, and single-ended up to 4 channels. And it's also integrated with high precision, 0.1% precision, with a very low part per million change of temperature coefficient. These precision resistors that you can use to build a resistive bridge to measure resistive sensors. And these are the 4 channels that are going to do the measurement. And also there are some jumpers that you can place in order to make use of these high precision resistors or not, depending on your application. And again, there's a number of these SDI12 headers and an external power selector for the external or the USB power. Same thing, there's USB chip here. May look a little different just because of different iterations of the chip. Doesn't really make a difference on the program. And that's the main processor. This is the most compact way to have high resolution analog inputs. Something, for example, if you want a sensor that outputs a fraction of a volt as an analog input, something such as a basic analog sensing will not be able to get you accurate result. This will do. It not only has a high resolution analog input, 16-bit, it also has an auto scale feature and a programmable gain. So if your voltage is small, then it'll actually enable the programmable gain to have the highest gain that it can get to read the input so that the result will be as accurate as possible. So again, this one's very compact. It gets you the SDI12 sensors and also the analog. The analog reads the same way as the SDI12 sensors. So the sensors may have addresses 1, 2, 3, 4, A, B, C, etc. The analogs will have the address of Z. Z is the lowercase z, which is the onboard sensors. So you use the same exact syntax to read the onboard inputs and the SDI12 inputs. Okay, so now let's move on to the next one. This one is the more expensive one. This is the USB SDI12 plus GPS module. So this is for more or less for mobile data collection. If you want to mount a bunch of sensors on, such as a boom of a tractor, you can collect your data as you collect your GPS information, and this is not expandable either, but this actually has plenty. There's an SDI12 input and also the GPS. And the GPS module itself, it comes from, I wonder if you can see that. Okay, that's very tiny here. It says Adafruit. So this is a company in New York City. They're actually in Manhattan. They sell these breakout boards at $40. So that kind of explains why this overall price is higher, is because I need to source it from another company that just sells these boards, and then solder that together. So that makes this board a ideal case for mobile data collection. So now let's take a look at expansions. As I said, this one is expandable. So if you're getting expansion, for example, if you started with this analog, with maybe basic analog, and then soon realize, oh, that's actually not enough accuracy. So what do? Well, you add on one of these boards. So the board, if you look from the side, there's actually a set of female headers, and it also comes with this male header that you can solder onto the middle of this basic USB adapter. So once you're done soldering, and you can stack them together, and this add-on board also comes with a bag of hardware that can help you stack them together to the kind of the precise height of stacking. So now you have this stacked on top, and well, I know it's going to block some of that connections, but you can always unstack and then change these connections if you need to. But this adds on a 4 channels of analog inputs, the same exact feature as the top half of this USB SDI12 Plus analog adapter provides. The top half here, which is the precision resistors coupled with the analog, high precision analog input. That's the same exact thing, except that now you actually have the freedom to have as many as 4 of these, because each one can stay at a different address. Here's the address selector. It comes in pre-selected as address 0. So if you pop this one out, you can place it here. Say this is address 1, 2, and 3. So you can have as many as 4 of these stacked together, with up to 4x4 16 analog inputs at high precision. So that gives you enough to expand. And also there's these optional SDI12 headers that you can have. But the warning is, well, if you already have 4 sensors over here with a bunch of wires, having additional sensors, it's not electrically impossible. It's possible to do that, but it will be difficult to manage the wires, the cable. The best way to do it is to limit the number of sensors that will actually have to wire to one board. So whenever you need to troubleshoot or remove a problematic sensor, it makes it easier. You identify which one it is on which stack, then you remove it. If you end up having too many all around, it'll be difficult to manage. Okay, so that's for the analog feature. If you want the high precision analog feature added onto this board, and you also, for example, you want a ring gauge counter out of these digital inputs, that would be a perfect combination. Up to 4 of these boards can be stacked together. But what if you want some extra SDI12 without having the analog. So here's the extra SDI12 extension board. So it also comes with the same thing with the hardware here, and also the extension board stacking headers for you to solder on the original board. The difference is it's got these SDI12 headers already populated, so you can just stack on and add additional SDI12 sensors as you go. And you may realize these two boards look very similar. That's right, the boards look almost the same. So I use the same circuit board. I just don't populate any of these components, but I populate these headers, and that makes it good for extension. And again, I recommend doing no more than 2 of these extension boards with a total of no more